Hello, I'm Junior Kwok, and today I'm going to introduce about Anton Zeilinger's experiment in 1998. After Bell's discovery that EPR's implication to explain the correlations using hidden parameters would contradict the predictions of quantum physics, a number of experimental tests have been performed. All these experiments confirm that the predictions of quantum mechanics is right. However, from a strictly logical point of view, they don't succeed in ruling out a local realistic explanation completely due to two essential loopholes. The first loophole is that the all experiments so far detect only a small subset of all pairs created. So, it would be necessary to assume that the pairs registers are a fair sample of all pairs emitted. The second one is that the directions of polarization analysis were switched after the photons left the source. The assumption of locality in the derivation of Bell's theorem requires that the individual measurement processes of the two observers are separated. Such an individual measurement then has to be so quick that it is impossible for any information about it to travel via any channel to the other observer before the measurement is finished. Selection of an analyzer direction has to be completely unpredictable, which requires a physical random number generator. Furthermore, to achieve complete independence of both observers, the individual events should be registered on both sides independently and compared only after the measurements are finished. Next, I'm going to talk about how the experiment was designed. In this experiment, any mutual influence between the two observations is excluded within the realm of Einstein locality. To achieve this condition, the observers, Alice and Bob, were spatially separated by 400 meters, which means that the individual measurements, as defined above, had to be shorter than 1.3 microsecond, the time for direct communication at the speed of light. They used polarization and tangle photon pairs, which were sent to the observers through optic fibers. The difference in these fiber lengths was less than 1 meter, which means that the photons were registered simultaneously within 5 nanoseconds. Each of the observers switched the direction of local polarization analysis with the transverse electro-optic modulator. Its optic axis was set at 45 degrees with respect to the subsequent polarizer. Applying a voltage causes a rotation of the polarization of light passing through the modulator by an angle proportional to the voltage. The modulation systems, which means high voltage amplifier and electro-optic modulator, as you can see in the picture, had a frequency range from DC to 30 MHz. The actual orientation for local polarization analysis was determined independently by a physical random number generator. The total of the delays occurring in the electronics and optics of a random number generator, sampling circuit, amplifier, electro-optic modulator, and avalanche photodiodes was measured to be 75 nanoseconds. This is much shorter than 1.3 microsecond, that any information about the other observer's measurement would have been retarded. The photons were detected by silicon avalanche photodiodes with noise of a few hundred per second. This is a very small amount, and the pulses of each detector were fed into electronic circuits responsible for disregarding events that occurred during transitions and encoding the position of the switch in an extra signal. Finally, all the detections were time-tagged in special time interval analyzers with 75 picosecond resolution and 0.5 nanosecond accuracy. So this is the result of the experiment, and it shows that the quantum theoretical predictions are confirmed. However, unlikely, local realistic or semi-classical interpretations are still possible, but we would have to assume that the sample of pairs registered is not a faithful representative of the whole ensemble emitted. Thank you for listening to my presentation.